So now we'll be talking about limits involving infinity. What actually happens as you let x get closer and closer to some number and the limit doesn't exist, or is what we call infinity, or letting x go to infinity or negative infinity. So we're going to first talk about letting limit as x goes to some number and see what happens. So the limit as x goes to 0 of 1 over x to the 4th, actually, we could say that this does not exist because you put 0 in there and you get, if you do it numerically, you're going to get bigger and bigger and bigger and bigger and bigger numbers. So we can say it does not exist. Or you can say it actually is infinity. And so we can actually define this as being the limit as x goes to a of f of x equals infinity, means that the values of f can be made arbitrarily large by taking x sufficiently close to 0 but not equal to 0. Or actually n, a, not actually equaling a. Not to be 0 always. So that being the case, we can have these nice low limits of things doing things and getting closer and closer and closer to some a value. And we can say it goes to infinity. So as an example, we've always said you can't divide by 0, but really 1 over 0 is infinity. Similarly, you can talk about the limit as x goes to a of fx is negative infinity, or the limit as x goes to a from the right is infinity or negative infinity, or from the left is infinity, negative infinity. So you can do both of those. This allows us to talk about a line called x equals a. It's called a vertical asymptote of y equals f of x if at least one of the following is true. If the limit as x goes to a of fx is infinity, if the limit as x goes to a of fx is negative infinity, if the limit as x goes to a from the left is infinity or negative infinity, and from the right is infinity or negative infinity. So when you define vertical asymptotes in the past, we didn't be this exact with the definition, but the definition really is about the fact that we can't have these limits existing. The limits have to go to infinity or negative infinity. So let's find the vertical asymptotes of this function and see if we can come up with the answer. In your previous math classes, you were told just find out whether the denominator equals 0, and then those are your vertical asymptotes, but they're not always your vertical asymptotes. They're possible values of your first vertical asymptotes. So possible vertical asymptotes is, and I get tired of writing vertical asymptotes, so you'll see me write VA for vertical asymptotes, is x equals 2 or x equals negative 2. So now, by the definition of a vertical asymptote, in order for it to really be a vertical asymptote, the limit, and let's just pick one of them, let's pick 2. So let's look at the limit as x goes to 2 of my function. And if that limit is infinity or negative infinity, everything is good and we can call it a vertical asymptote. So let's take the limit as x goes to 2 of x squared plus 2x over x squared minus 4. So using direct substitution, if I plug 2 into the top, I get 2 squared, which is 4, plus 2 plus times 2, which is 4, so I get 8 in the top. In the bottom, I get 2 squared, which is 4, minus 4, which is 0, so I get 8 over 0, which is, in fact, infinity. So everything's good. That means that x equals 2 is a vertical asymptote. Now let's do the exact same thing with x equals negative 2. So let's take the limit as x goes to negative 2 of f of x. So that would be x squared plus 2x over x squared minus 4, taking that limit. Using direct substitution, if I tried to plug it in there, I'm going to get 0 on the top and 0 on the bottom. Again, that's an indeterminate form, and I can't just say, I don't know what it is. That's why it's called indeterminate. So let's do some algebra on this one. Let's take the limit as x goes to negative 2. Let's factor the top. That factors as x times x plus 2. Let's factor the bottom. That factors as x minus 2 and x plus 2. And then we can see we can cancel some things. The x plus 2 and x plus 2 cancels. So that's cool. So now that means that we're going to have the limit as x goes to negative 2 of x over x minus 2. And that happens to be negative 2 over negative 4, or 1/2, which is not infinity or negative infinity. So that tells me that x equals negative 2 is not a vertical asymptote. Okay, cool. So that's what you have to go through. You actually have to prove that they're the case. You can't just decide they are without having proven it. These, again, were just possible places of vertical asymptotes. Now you must actually prove that the limit is, in fact, either infinity or negative infinity. If it's not a vertical asymptote. This gets us into a concept of what we call end behavior. End behavior is what happens as x becomes really large, or for that matter, if x becomes really, really small. So using this same function, if I were to graph this up, you can see we've got our x equals 2, vertical asymptote, x equals negative 2. You notice you don't have a vertical asymptote. But you can see that the end behavior, as x is getting really, 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 really big, we're heading towards some value. So this is what we know call the end behavior. So it's looking at what is the limit as x is going to infinity of f of x. And it looks like from this graph that it's about 1. So in other words, as I'm letting x get bigger and bigger and bigger, I can see that my y values are going to get closer and closer and closer to the number 1. And that's all it's saying. By the way, it works the other way too. You can get really, really small. Going to negative infinity, you can see you're also going towards the number 1. And so this gives us the idea of what we call a limit. So let's actually do this first. Let f be a function defined on some interval from a to infinity. Then the limit as x goes to infinity of f of x equals L means that f of x can be made as close to L as we like by taking x sufficiently large, or again, sufficiently small. So going back to this graph, we're saying that the limit is 1 because we're going to let x get really, 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 really big and seeing what we're heading towards. Or really, really, really small. This is actually the definition of what we call horizontal asymptote. The line y equals L is called a horizontal asymptote of my function if either the limit as x goes to infinity of f(x) is L, or the limit as x goes to negative infinity of f(x) is L. So as an example, the limit as x goes to infinity of 1 over x is 0. So, and for that matter, the limit as x goes to negative infinity of 1 over x is 0. So it actually says that 1 over infinity is 0, though we don't really think of it that way, but you can kind of think of it as that's what happens. That also reminds me the limit as x goes to plus or minus infinity of 1 over x to the n, as long as n is some positive integer, is always 0. I'm going to use these properties later to do some simplifying. All right, so let's actually go find some horizontal asymptotes. So that means what I want to do here is I need to find those limits. So I'm going to go ahead and now look for the limit as x goes to infinity, and I'm going to use infinity because it's a little bit just easier in my mind to use positives than negatives. And we're going to take the limit as x goes to infinity of x squared plus 2x over x squared minus 4. Well, looking at this, I can't just put infinity in there because I get infinity squared, which is infinity, plus 2 times infinity, which is infinity, and infinity plus infinity is infinity. And I get infinity squared minus 4, which is still infinity, and infinity over infinity is who knows what. It's another one of those indeterminate forms of what we can't actually find out what it is right now. So we need to do some algebra here to try to simplify this a little bit. And I want to use these properties here. I want to use the fact that the limit as x goes to infinity of 1 over x to the n is 0. So I need to get x's in the bottom. So one of the things I notice is I have x squared as my highest degree of x. So what I'm going to do is I'm going to divide every single term by x squared. So I'm going to take each one of my terms here. I'm going to divide each one of those terms by x squared. And I can do this because I'm just dividing by the number 1. I'm dividing 1 over x squared, and I'm multiplying 1 over x squared by the top and 1 over x squared by the bottom, which means I'm just dividing by the number 1. So I can do this, and there's no problem with this. So now that I've done that, let's see what we get. We get the limit as x goes to infinity of 1 plus 2 over x. And I use the highest degree of x because then things will cancel like this. And I get 1 minus 4 over x squared. So using limit laws again, the limit of a constant is always 1. Doesn't matter what limit we're heading towards, the limit of 1 will be 1. The limit of 2 over x as x goes to infinity, again, we're using the limit laws, so we can divide all these things up into limits of each individual piece. This property right here just told us that the limit of 2 over x is 0 as x goes to infinity. So that means that this is plus 0. And we're going to have 1 minus 4 over x squared as x goes to infinity is also 0. So we end up with 1 over 1 or 1. So that tells me that my horizontal asymptote is in fact y equals 1, because the limit as x goes to infinity of my function is 1. Let's find this limit. This one's not asking to find horizontal and vertical asymptotes, but similar concept. We're going to go ahead and do this. We're going to find this limit. We do the same thing. We're going to divide through by the highest degree of x. The highest degree of x looks to be x cubed. So we're going to take the limit as x goes to negative infinity. We're going to take each term and divide each term by x cubed. And again, we can do that because we're just dividing by 1. So we're going to have x cubed, x cubed, x cubed, x cubed, and x cubed. So now that we've done that, we're now going to have the limit as x goes to negative infinity of 1 over x plus 2 over x cubed, 1 plus 1 over x minus 1 over x cubed. So using our limit laws that allow us to take the limit of each individual piece, the limit as x goes to negative infinity of 1 over x, using those other properties, is 0. The limit of 2 over x cubed, using those other properties, is 0. The limit of 1 is 1. The limit of 1 over x is 0. And the limit of 1 over x cubed is 0. So we end up with 0 on the top over 1 or 0. So that's the limit, is 0. Let's do another one. Let's do this limit as x goes to infinity. In this case, I again want to divide by the highest degree. In this case, I have a t. I have a t squared, but that t squared is under a square root. So I actually have the square root of t squared, which is t. So my highest degree is actually t. So we're going to divide every single term by t. But when you take that t into your square root, so we're going to divide by t, we're going to divide by t. If I take this t inside the square root, it becomes t squared and t squared. So that gives me the limit as t goes to infinity of 1 plus 2 over t over top of the square root of 9 plus 1 over t squared. Now again, using your limit laws, take the limit of each piece. Limit of 1 is 1. Limit of 2 over t is 0. Limit of 9 is 9. Limit of a square root, you can take the square root outside of it, basically. And the limit of 1 over t squared is 0. So we get 1 over the square root of 9, which is 3. And so your limit is 1/3. We can also let x go to infinity or negative infinity. There's no reason why we couldn't do that. So we can let x go to negative infinity. That would be e to the x. Remember the limit as x goes to negative infinity of e to the x is 0. If you don't believe me, look at the graph of it and you'll see that that's where it's heading. The limit as x goes to infinity of e to the negative x is 0. Again, looking at the graph, you'll see that's where it's heading. So I'd like to find the limit as x goes to infinity of e to the negative x squared. So this isn't as straightforward as what we had before because we have this, we have these forms up here that just involve x. So we're going to let t be that negative x squared. So let's let t be negative x squared, which means that this becomes the limit as e to the t, because we're just letting t equal negative x squared. So we're just replacing that. But if I'm doing that, I'm also replacing the x here. So I got to think about where is that heading? And it turns out that if x is going to infinity and t is equal to negative x, then t is going to be heading towards negative infinity. So it'd be t to the negative infinity, which we know already is 0. Limit as x goes to infinity of f of x equals infinity means f of x gets large as x gets large. Similarly, limit as x goes to infinity of f of x equals negative infinity means that as x gets large, f of x gets really small, and all the rest of these. And those are limits involving infinity.